we have a pulley of mass m and moment of inertia I. You know, I equals to ICM plus MD square. ICM is given. When the axe passes through the object, we have ICM. D is the distance between the center of mass of the object, of the pulley, and the axis, which is equal to 0 in this case. So I equals to ICM. If we have a rotation anticlockwise at time t, we have omega as angular speed and alpha as angular acceleration. If we choose a small element here, element A, and here we have a small element B. So the velocity at the time t, the velocity of the element A equals to Ra times omega. And the velocity of the point B of the mass B equals to Rb times omega. And you know, VA and VB are tangent to the trajectory. If we have a rotation, B will rotate around the axis with a radius equals to Rb, and A also will rotate around the axis with a radius equals to Ra. VA and VB are tangent to the trajectory. As you see, here we have VA and here we have VB. Okay, what about the A tangent? A tangent of the point A equals to Ra times alpha, and A tangent of the point B at the time t equals to Rb times alpha. A tangent and V have the same direction, so we can say VA and A tangent and VB and A tangent of B. Here we have A tangent A, and here we have A tangent B. Okay, what about the kinetic energy of A and B? You know, the here we have a rotational kinetic energy of A and B. The kinetic energy of A equals to I of A divided by 2 omega square. And also the kinetic energy of the small element B equals to I B divided by 2 omega square. What about IA and IB? You know, if the axis doesn't pass through the element A, so we don't have ICMA 0 plus M of A times the distance between the mass A and the axis equals to RA square. The same for IB equals to 0 because the axis doesn't pass through the point B plus MB RB square. What about the total kinetic energy of the system, of the pulley? The kinetic energy total of the pulley, as you see, we have a pure rotation. So we have I total of the pulley divided by 2 omega square. I total equals to ICM of the pulley divided by 2 omega square. That's all about the small element and the total pulley. Now, let's say we have a mass M1 here is attached to the pulley by a cord passing through the point A. In this case, the velocity of the mass M1 equals to the velocity of A. So we can say VA equals to, no, V1. Here we have V1 is down. V1. V1 equals to VA, and VA equals to RA omega. And also the acceleration of M1, you know, it's down. We have A1. Also, as M1 is attached directly to A, they have the same acceleration. So A1 equals to A of the point A equals to RA times alpha. If we attach a block through the point B, here we have M2. So we can apply the same calculation. Here we have V2 and we have A2 acceleration. We can say V2 as M2 is attached to the point B, so VM2 or V2 equals to VB. So V2 equals to VB equals to RB times omega. And the same about A. You know, A2 equals, here we have tangent, okay? A2 equals to A tangent of the point B, which is equal to RB times alpha. What about the kinetic energy of M1 and M2? The kinetic energy of M1, here we have a linear motion. We don't have rotational motion. Equals to M1 divided by 2 V1 square. We can substitute the value of V1, which is equal to VA equals to RA omega. So we can write M1 divided by 2 RA omega square. And the same for the kinetic energy 2, which is a linear motion. We have M2 divided by 2 V2 square, and V2 equals to VB equals to RB omega. Square. Okay, we can add a point. If we apply the Newton's second law on the mass M1, okay, we can write for M1, we have M1G is down, minus T is up, equals to M1 times A1. You know here, A1 equals to A tangent of the point A, which is equal to RA alpha. So we can write here M1 times RA alpha. And the same for the mass M2. If we apply Newton's second law of the mass M2, we have M2G down, M2G minus T prime. Here we have T prime equals to M2 times A2. A2 is attached to AB. They have the same. So we can substitute the value of A2 by RB alpha. So we can write M2 times RB alpha. Okay, this is a simple relation between the velocity and the acceleration of M1 and M2 with the angular speed and the angular acceleration of the pulley. Okay, I can add a small point. If you apply the conservation of mechanical energy, for example, mechanical energy initial equals to mechanical energy final. Let's take initially we have omega initial and we have alpha initial. And finally, we have omega final and we have alpha final. You know, the initial kinetic energy equals to, we have the kinetic of M1 plus the kinetic of M2 plus the kinetic of the total pulley. So we can write equals to M1 divided by 2 V1 square plus M2 over 2 V2 square plus I of the pulley divided IP of the pulley divided by 2 omega square. Okay, I of the total pulley, which is equal to ICM of the disc of the pulley. This is about the initial kinetic energy. We have V1 initial, okay, and we have V2 initial. And as the final kinetic energy, we can write kinetic energy final equals to M1 V1 final square divided by 2 plus M2 over 2 V2 final square plus IP, we have the same I divided by 2 times omega final square. Don't forget here we have omega initial square. Okay, this is about the kinetic energy. And you know, we can substitute V1 initial. If you come here, V1 initial equals to VA initial equals to RA times omega initial. And V2 initial equals to VB initial equals to RB times omega initial. And you apply the same for V1 final and V2 final. V1 final equals to VA final equals to RB times omega final. And the same for B. I want to add the last point. I want to apply for the rotational motion object summation of tau equals to I times alpha. Let's say we have at initial time t initial, we have alpha initial. Okay, here the total F applied on the pulley at the point B. Here we have the mass M2. So at the point B we have T2, at the point A we have T1. Here at the axis we have the weight of the pulley, and we have the reaction up, N mg. You know that tau of mg equals to tau of n equals to O. Why? Because n and mg pass through the axis. They don't have any effect on the rotation. What about T1 and T2? Here I take the positive direction anticlockwise. T1 turns the object in the positive direction. T2 also turns the object in the positive direction, down and down. So we have plus tau of T1 plus tau of T2 equals to I alpha initial. Now I calculate the value of tau at initial time. Okay? You know from this relation here, A1 equals to A tangent A equals to RA alpha. So we can say A1 initial equals to RA alpha initial, and A2 initial equals to RB times alpha initial. So we can substitute the value of alpha I. You know alpha I equals to A1 initial divided by RA, or alpha I equals to A2 initial divided by RB. We can substitute the value of alpha initial, this one or this one, in terms of A1 or in terms of A2. We can put it here.